Good morning. My name is Sotner. I'm from Brno University of Technology, and my pleasure is to chair this session now. So we have 90 minutes for a full session. So for each presentation, I suppose 10 minutes for introduction of the work and 5 minutes for discussion. And I will manage time requirements if there will be some issues with overlying and so on. So the first presenter of this session is Lukas Langhammer from Brno University of Technology in Czech Republic with a paper titled Dual Mode Multifunctional Reconnection-Less Reconfigurable Filter. So Lukas, you have word. Please share your screen for us.
Thank you, Mr. Chairman, for the introduction. I'd like to...
And then full screen, please.
Okay. So just give me a second to prepare. So, hello everyone. The research I would like to introduce here is dealing with reconnection-less reconfigurable filter working in multiple modes. So there's a bit of theory to start with. Frequency filters can be divided based on the fact whether they do or do not provide the feature of reconnection-less reconfiguration. If they do not provide this feature, we are usually talking about filters having multiple inputs and single output, so-called mesofilters, or the other way around, filters with single input and multiple outputs, semofilters. In this case, in order to provide a different type of the transfer function, we need to choose or switch between the inputs and outputs of a given structure and possibly use their combination. Other possibility are filters with one input, one output, so-called CSOFI filters. But in this case, if the filter is supposed to provide a different transfer function and it doesn't offer the feature of the reconnection-less reconfiguration, a structure modification is necessary. Electronically reconfigurable filters or reconnection-less reconfigurable filters, on the other hand, can change the resulting output response depending on the setting of electronically controllable active elements, such as operational transconductance amplifier, adjustable amplifier, and others. So the resulting output response is depending on the setting of electronically controllable parameters, can be transconductance, voltage gain, current gate, and so on. And there's some basic information about the proposal itself. It's based on voltage gate differencing transconductance amplifier, variable gain amplifiers, and adjustable current amplifiers. It's working in the current mode, voltage mode, and also in the mixed mode, voltage to current transfer to be specific. It provides all standard transfer function of the second order and also special functions of high pass and low pass functions with transfer 0. All these functions are available for both current mode and voltage mode, and all the functions are available by a specific setting of either current gains or voltage gains. Electronic control of the pole frequency and the quality filter is also available. And there's also a useful feature of adjustment of stop band and pass band area of available functions, as will be shown later. To support the design, a piece-by simulation using CMOS 0.18 micrometers process were carried out. The following two slides will present used active elements. Mainly it's voltage differentiating transconductance amplifier, which creates the core of the filter. There's the schematic symbol, its inner structure based on two operational transconductance amplifiers, and this matrix describes the behavior of this active element. Other used active elements in the proposal are adjustable current amplifier and variable gain amplifier. This slide presents their schematic symbols, relations describing their behavior. Adjustable current amplifier has been created by EL2082 device, and VGA then by VCA 822 device. All these devices are commercially available. And this is the structure of the filter itself. It consists of one VDTA, 3 variable gain amplifiers, 3 adjustable current amplifiers, and 1 counterforwarder. There are also 2 capacitors where C2 is grounded and C1 is then grounded through the voltage output of the VGA1, considering the fact the voltage output has 0 impedance in the idle case and very low impedance in the real case. Of course, it depends on the specific implementation of this active element. These two relations describe the transfer function of the filter. The first one in case of the voltage mode, the second one for the current mode. And from these relations, you can see we can change the output resulting transfer function. The output response depending on the setting of voltage gains A1, A2, and A3 for the voltage mode, and its current gains B1, B2, and B3 in case of the current mode. So depending on the setting of these parameters, we can cancel some terms of the numerator. And what specific function we can obtain depending on the setting is specified in the table down here. It's specified in this case for control voltages, so it's either V set A or V set B. And to understand the function of the control voltages, -1 volt is equal to 0 transfer, 0 volts is equal to unity gain, transfer equal to 1, and 1 volt is equal to transfer of 2 in case of the voltage mode. And for the current mode, it's either 0 volts for 0 transfer and 1 volt for transfer of 1. Let's move to the simulation results. There are the simulation results of transfer function, high pass, low pass, band pass, and band stop in case of the current mode. The simulation results are compared with the theoretical expectations. Those are the black dashed line lines. And you can see the simulation results are in good agreement with the theoretical expectations, except for high frequencies, whereas you can see the effect of parasitic characteristics of used active elements or the simulation models of used active elements. The same transfer function, again comparing the simulation results with the theoretical expectations, but this time for the voltage mode. Other thing, as mentioned before, the filter offers the electronic control of the pole frequency, quality factor, and the pole frequency can be controlled by changing the transconductance GM1 and GM2 as long as they are equal to each other, so they won't affect the value of the quality factor. And the pole frequency, or the control of the pole frequency has been tested in case of voltage mode, band stop function for 5 different settings. So down here in the table, we can compare the results obtained from the simulations and with the theoretical expectations, and you can see the results or the numbers are quite close to each other. So it supports the function of this feature. Other usable feature is controlling the stop band area of available functions. That's demonstrated here for current mode bandpass function. And as you can see, we can control the level of stop band area at low frequencies by setting current gain B1 and its current gain B3 for band stop area at higher frequencies. So in general, we can control the stop band and also pass band area of available functions depending on our needs. And finally, the conclusion. So to sum the features of the proposed filter, it provides function in the current mode, voltage mode, and also mixed mode. It's 16 functions in total. Piece-by simulations were carried out to support the design, and the filter, the paper itself also offers the sensitivity analysis and the analysis of the dynamic range of the proposed structure and the electronic control of the pole frequency, quality factor, and stop band or pass band area are available for this design. That concludes my presentation. Thank you for your attention.
Thank you for your contribution, Lukas, and I can open a discussion. If there are some questions, please, colleagues, ask. We can discuss. So if no question from my audience, I can ask you, what is the most important device, active device, where are concentrated frequency limitation of your solution?
Well, if I will go back to the structure itself, all active elements should be having their bandwidth up to around like 50, 70 megahertz. The biggest problem probably for this design is the output or the impedance of the voltage output in case of VGA1, because it's depending how the capacitor C1 is going to be virtually grounded or not. So it can cause the problems, or the filter can be unstable. So that's probably the most important part which can affect the results.
So increasing output impedance with frequency.
Yeah.
Thank you very much. So any questions from the audience now? If not, I will thank you for your presentation, for your discussion, and we will move to the next paper. So I think the second presenter is not here, so we can move if we will be available later. So we can move to the presentation number 3, which has title Measurement of event-related brain potentials, amplitude, and latency based on digital stochastic measurement over interval. The presenter is Nikola Petrovic. So Nikola.
Hello all.
So words is yours.
Just a second, do you see me? I'm sorry, this is my first time using this.
Yeah, I can see you.
Oh, great. So my name is Nikola Petrovic, as I have said already, and today I'll speak about our work based on ERP signals. And now
so please share your screen first of all.
Yes, of course. Just let me share my screen and okay. Okay, sorry, just a second.
Yeah, it's starting to work. Thank you.
So you can see now the. Okay, let me just alter. Just a second. Sorry. Okay, you see the presentation. It's. Is it working? So we can start. Okay. First of all, hello to all participants. My name is Nikola Petrovic. I'm a PhD student at Faculty of Technical Sciences, University of Novi Sad, as well as scholarship of Visegrad Fund Scholarship. Today, I'll present a measurement of event-related potentials, amplitude, and latency based on digital stochastic measurement over interval. Now, as one aspect of cooperation between Bialystok University of Technology and Novi Sad University under Visegrad Fund Scholarship, we have developed multiple systems for measurement of biophysical signals, as well as calibration systems. This team consists of professors, assistants, students, such as me. I am just a PhD student. And we have developed multiple applications from these systems, from brain computer interface systems, which are useful for many applications in the field of medicine, assistive technologies, and I'll speak about that later, but now let's focus on the main part. Firstly, about EEG and ERP. Electroencephalography is measurement method used to measure voltage potentials of central nervous system, and usually it's non-invasive. Of course, in this part we used non-invasive electrodes, and EEG is non-stationary signal, which means that EEG also is a signal which need to be processed. And now if we speak about EEG, we can see that there are many specters. For example, we have divided, usually it is divided in 5 ranges. First one is delta, it's from 1 to 4 hertz. Second one is theta, and it is from 4 to 8 hertz. After that is alpha, which is 8 to 12 hertz, and beta is 12 to 30 hertz, and gamma is about 30 hertz. All of these factors gives us information, but these informations are not always useful for experiments and signal processing that we are doing. So we are now speaking about ERP, which means event-related potentials. So this term was firstly used at 1969, and it means that our brain responds to activities and events, as the name says, in our environment and to our, for example, movements. It was firstly described as that. Of course, after this, event-related potentials started showing different types and applications, which means that we had event-related potentials about just thinking about movement, just to say it like this. If we want to get one ERP, we have a problem because it is low amplitude and low frequency signal, and we need to get it out of our EEG. In order to do that, we need to get thousands of signals and epochs in order to get just one ERP. And as you can see on this picture, there is one example of ERP where we have took ERP from PZ, it's parietal lobe, from parietal lobe signal, and because it's most easy way to get EEG from there, because it is where the motor cortex is, but not talk about neurological part here. And ERP, as you can see, is marked on this part. So basically, what is crucial part is that in order to record ERP and detect, we need to suppress other parts of signal. And in this paper, we have published how we have done it with digital stochastic measurement over interval, or DSMI, which I will explain right now in the next part. So a DSMI is a part, just a second, water. DSMI method was developed in order to measure precisely signals with low precise components. In this part, it means that we were using, for example, low bit analog digital converters, etc. But I'll speak on the next slide. There is an example. Basically, it means that we are adding jitter to the original signal, and after that we are measuring how many changes there are in this signal. After that, we are giving it to the AD converter, and after that, multiplying. So let me show you next slide. Here you can see, just a second, let me use my pen, laser pointer. As you can see, this part here is the crucial part of DSMI, which means that we are to the original signal, we are adding jitter, and after that we are doing analog digital converting. After that we are doing normalization on the interval of measurement, and after getting these values, we are multiplying it with another signal. In this type, if we, for example, use the same signal, we'll get values. We'll get values power of this signal. I'm sorry, maybe I didn't use the right word, but let me continue. And after multiplying it, we are giving it to the accumulator, where we can see what is the amplitude of the first signal. This whole thing, of course, we are using this whole system in order to measure one Fourier coefficient of our signal. And in this part, as you can see, we are using two analog digital converters. In order when we need, for example, 30 Fourier coefficients, it is not that easy to build this system, and because of that, we just used method of this system and developed it on program level, which I'll explain on next slides. This is just part of our crucial system parts. Now, speaking about ERP lab, which is also used in our work, ERP lab we have used in order to get our signal amplitude and latency on different number of epochs. As I mentioned earlier, we need more epochs in order to get ERP, because ERP is low amplitude and low frequency, which means that we need to average 10 or thousands of these epochs, which is in practice not a very easy job. For example, one epoch is lasting from 1 second to 8 seconds, and we need we need to complete measurement with 100 or 300 EEG epochs, which means that we need 40 minutes of measurement. Let's be honest, it's not a small thing. And in order to get this done, we have used ERP lab as one part of our project, which means that ERP lab was dedicated to process all these epochs, but digital stochastic measurement was implemented also in MATLAB, but using another scripts and another part which we have developed here. And of course, in order to develop this, a real measurement would last very long. For example, as I said, this type 40 minutes, but with optimization of simulations, we had possibility of simulating these measurements and get our system working on a different way. So the whole point is that we had a possibility of simulating this system and getting these values in a simulation, which provide us possibility to implement other parts. But I'll speak about that in conclusion. Let's just focus on the main part of our system. As you can see on this picture, we have developed this whole system where you can see raw EEG is given to ERP lab. After that, firstly processed, but after that given to ERP lab, where we are processing EEG. After that, we are getting average at ERP amplitude and latency. And in main program, we have digital stochastic measurement implementation, where we do comparison how does the system work and how do we get these ERP signals, which is the main part. That is the, as I explained earlier, these are all previous parts that we used. So speaking about results given from this developed system, we have, as you can see here, presented two results. Unfortunately, I couldn't put two slides together, this one and next. Here, of course, there are small differences between first and the second graph. On the left, you can see usage of this system with 30 epochs. And on the right, you can see a system with 15 epochs. So as you can see, differences are small, and of course there you can see them in those amplitudes that are higher with higher frequency on this part and on this part, as you can see. Of course, which means that one implementation of system which measures 15 epochs of 15 Fourier coefficients and one with 30 Fourier coefficients are working similar. And on this slide, you can see that we are getting latency time error, relative latency time error, similar and very small, which is crucial for us. For example, when we are developing BCI system, brain computer interface system, we need to get a relative error of latency time as low as possible, which is the main condition. But amplitude is in the second part. And as you can see, relative error of amplitude are also close, but not that small. Of course, there is a question now, is the more better? Is it good to use a system with 15 Fourier coefficients or 30 Fourier coefficients? Of course, it all depends on what we need and what we want. And because of this, we have developed optimization system which provides us best results with optimized resource use, which means that we are using computational resources at the best level and designing system with a less possible number of components. So as a conclusion of this work and this cooperation that I have mentioned, we have developed a new system, which means that measuring digital stochastic measurement is used for ERP. That is what is new of this. And we have overcome the current problem as such is number of epochs. We have lowered the number of epochs for about 30%, and measurement time, of course, is getting lower because we have better simulations, which give us possibility to simulate these problems and these experiments. And also we have measurement time reduction because we can get better results to get in less time, the better results for real experiments. So I hope I wasn't boring and I got it all right. And thank you for your attention. Now, if you have any questions, please feel free to ask or send them by email or anything else.
Thank you, Nikola, for your interesting presentation. And I have to also ask the audience, if there are some questions, please unmute your microphone and you can ask. If not, I have some question for you. How are the noise effects in your systems? If there is some difference between the second question, invasive method or non-invasive method, which has influence of signal to noise ratio, it is observable.
Of course. First of all, I need to ask that we are always using non-invasive methods, because using invasive methods needs a lot of paperwork and it's not easy to do with people. And a second thing, yes, of course, we have different types of noise here. For example, it's not just noise from the outside. For example, a noise of electronic devices, but we have also noise from other cognitive algorithms that are active in the same moment from people. For example, if examinees are not well prepared and not focusing on their task, they'll we won't have such a good results as we would if they're focused on task and if they work well. I hope that I have answered your question.
Thank you very much. So if there are not questions from the audience, I can again thank you for your presentation, and we can move to another presenter. Please stop sharing of yours.
Thank you very much for your help and your opportunity.
And the next speaker is Ibrahim Selfik with the presentation entitled Small Motion Detection and Non-Contact Vital Signs Monitoring with Continuous Wave Doppler Radars. So,
hi everyone.
Hi, and what is yours?
My name is Ibrahim Selfik. I'm a research assistant in Konya Technical University, and I am a PhD candidate. Our work is small motion detection and non-contact vital signs monitoring with continuous wave Doppler radars. The content of presentation: first part, introduction; second part, principles of continuous wave radar; third part, measurement setup and signal processing; fourth part, measurement results; and last part, conclusion. Radar technology has been used for civilian applications since the mid-1970s. Especially in the last 20 years, it has been developed in terms of both hardware and software and adapted to all areas of life. From this situation, the medical field got its share. In the present case, vital signs monitoring is performed by contact devices such as pulse oximeters, piezoelectric sensors, electrocardiography, photofleximography, and respiration belt. These devices are uncomfortable for the patient. They cause extra injuries, especially in neonatal units and burn cases. Radars have been proposed to monitor vital signs for eliminating the disturbance caused by contact sensor. The use of radars in the medical field allows the patient to move freely. It reduces maintenance costs and is particularly convenient for medical professionals. Doppler radar is the basis of non-contact vital signs measurements. Many different studies have been put forward a few different radar types. Radar non-contact measurements are performed in cases such as sleep apnea problem, sudden infant death syndromes, elderly and patient home care, detection of lives under the earthquake debris, through wall live detection, and surveillance of the target. In this study, two continuous wave Doppler radars operating at 2.4 and 24 GHz are used. Firstly, small displacement motion due to a mechanism operating at a fixed frequency is detected. Then vital signs are found out utilizing a healthy human subject. The purpose of using two radars of different frequency is to determine how are frequencies of radars sensitive to small displacements. Figure 1 shows a block diagram of a basic continuous wave Doppler radar. A continuous wave Doppler radar transmits a sinusoidal wave to the target. The wave reflected from the target is received by receiving antenna with a tiny but meaningful time delay depending on the distance. The phase difference between the transmitted and received signal is directly related to the target movement. The signal transmitted from the radar is expressed in 1. The received signal expressed in 2. AR represents the amplitude of the received signal, and D0 is the nominal distance between the radar and the target. In addition, lambda is carrier wavelength, and XOT refers to the chest wall movement, including breathing and heart movement. Equation 4 shows the baseband signal output. The sensitivity of the radar depends on the nominal distance. This results in optimal and null point output of the radar. If beta is an odd multiple of P over 2 and XOT is much smaller than lambda, the optimum output phase demodulation sensitivity is achieved, and the baseband output is proportional to the chest wall displacement. However, beta is an even multiple of pi over 2 and XOT is much smaller than lambda. The sensitivity is very low. Null points occur and the output is no longer proportional to the displacement that changes over time. In order to eliminate this problem of the radar, a quadrature receiver system has been proposed. Figure 2 represents the block diagram of the quadrature radar structure used in the study. This system has two outputs that have 90 degrees phase difference from each other. These outputs are called in phase and quadrature phase. In 5, one of the outputs always indicates the optimum point. However, if beta is an integer multiple of pi over 4, it does not have optimum sensitivity at the two outputs, resulting in misinterpretation of motion. The arctangent demodulation solves this problem, and the phase obtained by combining the two signals is directly proportional to the target movement. The method can be written in 6. The operating frequency of the radar is an important factor for resolution. 4 pi XOT over lambda is the amount of phase modulation in radians, and XOT represents the target movement. As shown in 6, higher frequency means lower wavelength and greater phase modulation. The phase change in the respiration and heart rate calculated for the 2.4 and 24 GHz radars used are shown in table 1. Measurement setup and signal processing. Two radars operating at two different frequencies are utilized for the study. Radar 1 structure is created on a printed circuit board, whereas radar 2 is obtained by combining discrete components. The radar structures implemented for the measurements are shown figure 3 and 4. This slide shows the selected components for radars. Left side, radar 1, 24 GHz. Right side, radar 2, 2.4 gigahertz components. We are using it there. Signal processing, figure 5 shows flow chart of the algorithms. First of all, normalization is required for quadrature baseband signal of the 24 gigahertz radar. After that, both radars use arctangent demodulation to extract the phase information from basebands, and unwrapping is applied to the phase. The expression in 8 is used to obtain the motion signal E of t from the unwrapped phase information. In order to obtain vital signs, the motion signal is filtered by two separate high-order bandpass filters. The frequency bands of the filters used to obtain the respiration and heartbeat rate are 0.1, 0.5 Hz and 0.82 Hz respectively. Frequency information of respiration and heartbeat signals is obtained by applying FFT to the filtered signals. Autocorrelation is performed to increase periodicity before FFT. Finally, the rate of respiration and heartbeat per minute is determined. A target test mechanism which performs a small vibration at a fixed distance is set up. It is used to simulate chest wall motion by adjusting the movement to 8.5 mm and vibration frequency is 0.25 Hz. For measurement performed with radars, the mechanism is located at a distance of 1 meter from the radar. The measurement time is set to 60 seconds. As a result of the measurements, movement is determined as 8.28 mm and the vibration frequency is 0.244 Hz. Measurement results for radar 1 are demonstrated in figure 7. For radar 2, displacement is measures 9.03 mm and same vibration frequency as radar 1. Figure 8 shows the results. Relative error and percentage error of the results obtained from both radars with the target test mechanism are tabulated in table 3. Measurements are then performed on a healthy human subject for both radars. For both radars, the subject is seated 1.5 meter away from the radar antenna. Measurements are fulfilled for 60 seconds, whereon 501 finger pulse oximeter is used as respiration and heartbeat references. Another reference for respiration measurement is the counting of respiration during the measurement. Measurement results for two radars are given in figure 9 and 10. The upper and middle figures show I and Q radar signals, while the lower figures displays the movement carried out by the subject. The movement frequency of the subject measured by two radars is different, especially because the measurement occurs at different times with the same subject. This slide shows radar 1 measurement results. The respiration and heartbeat frequency are calculated FFT or respiration and heartbeat signal during the measurement period. The frequency of respiration is calculated 0.229 Hz and heart rate frequency is 1.251 Hz. Figure 11, figure 12 and figure 13 show that. This slide displays radar 2 measurement results. Frequency of respiration and heartbeat is calculated the same way as obtaining radar 1. Respiration frequency is 0.29 Hz. For heartbeat, this value is 1.541 Hz. After that, for two radars, the results acquired from the measurements performed with human subject and comparisons with reference values and error rates are given in table 4 for 5 measurements, radar 1 and radar 2. Conclusion: a low-cost radar is manufactured on a printed circuit board with the necessary circuit elements and commercial off-the-shelf radar. Another radar structure is implemented by combining discrete components. First, a small movement is detected with the help of a target test mechanism. For motion detection with radars operating at 24 GHz and 2.4 GHz, PEs are 2.58% and 6.23% respectively. PE for the vibration frequency of the mechanism is 2.4% for both radars. Experiments are then carried out with a human subject to acquire non-contact vital signs. For the 24 GHz radar, respiration rate and heartbeat rate are determined with PEs 1.85% and 6.17% respectively. These error values for other radar are 2.35% and 8.24%. From the measurement results, it has seen that the resolution of the high-frequency radar is better than the low-frequency radar. Measurement results indicate that radars may find a wider use in the field of medicine in the future. Thank you for listening my presentation.
Thank you, Ibrahim, for your presentation, and I can open discussion. If there are any questions, please ask. If not, a very short question from me. Are there some distance limit between the body and spot or antenna of the radar?
Yeah? I don't understand.
Are there some distance limit between the body and the antenna of the radar?
Yeah, we are attention this situation, and we
For
set
example,
set up this situation, and 1 point meter select.
1 point meter, yeah, also used in the test. Thank you.
Thanks.
So if there are not any questions, again, thank you for your contribution. Very good presentation. And I will ask the next presenter, which is the Pablo Corral, with the contribution titled Implementation of an AFDX interface with Zinc SoC board in FPGA. The authors are mainly from Spain. So Pablo, please, you can start your presentation. Switch unmute. Thank you.
Roman, thanks. Sorry. Yes, my presentation. Sorry, no.
Yeah, it's working. We can see it.
Yeah. Okay, it's okay. Yeah. The title of my presentation is Implementation of NAFDX interface with Zinc SoC board in FPGA. So the main parts of this work are, the main part of this work are introduction, where we describe AFDX, a state of art, where we define two new parameters related to aircraft networks, with a special emphasis in bandwidth allocation gap, jitter, and AFDX frame. Next section is work environments, with information about the hardware used in the topology for the AFDX test. In test results, tests have been created in software in order to validate the whole system. So we validate TX frame format validation using a demonstrator based on AFDX message exchange between simulated end systems. After that, we tested latency measurement through the CATX tool, and we tested. Well, have a problem with my mouse. And we tested FPGA footprint measurement too. Finally, in conclusion, we analyzed the obtained results. Sorry, a problem with, I think is the, yeah, now it's correct. Yeah, so and this work is based in the hardware development of a transmission part for the communication inside the satellite. So our goal is move as much as possible of the software part into the FPGA matrix due to the single event upsets. So this project is part of the collaborative project called Mission NetSpace, and it was chosen by the European Commission under the 7th Framework Program for Research, FP7, to develop an AFDX demonstrator based in FPGA. It has to be able to receive and transmit frames and enhance their robustness. AFDX, avionics full duplex switched Ethernet, is a trademark of Airbus and a specific implementation of Air Inc., Aeronautical Radio Inc. Specification 664 Part 7. AFDX is a deterministic network based on the same hardware as Ethernet, IEEE 802.3. So, state of art. AFDX added 2 new parameters related to aircraft networks, if we compare with the previous version. So first of all, an AFDX switch with similar characteristics to LAN switches and the end system responsible to send and receive the data to from the network. AFDX switches are the device developed to connect the end systems between them or with other switches together, and to check that the key parameters like delivery, latency, and jitter that are inside on one specific range. This task creates a big overhead compared to Ethernet switches. So this is the difference, yeah? And it slows the switching speed down. The main topology used with AFDX switches and end system is a star formation. The other part is the AFDX end system. These systems are designed to work as a receiver, transmitter, or both, and they make use of the final network. Every end system is capable to support multiple applications that can connect to the AFDX network. So, back, the bandwidth allocation gap is measured in milliseconds, and it defines the period of a VL. VL is a virtual link, and sets so the maximum amount of packages which can be sent in one sending period. It's about 128 milliseconds. The back number has to be, by design, an element of powers of 2 until 128. Setting back equals 2 permits the VL to send 64 messages in one period. All these messages are equally distributed and have to be sent at the right moment within a maximum jitter of 500 microseconds. So the AFDX standard also introduced a jitter for every end system, and that is the other part, the important part, the jitter in every end system. The jitter is a deviation of a theoretical sending time, depending on the amount of transmitting virtual links and their backs. An end system will have a certain amount of jitter. This largest jitter of 500 microseconds is fundamental to this demonstration of determinism for AFDX. So the most difference between AFDX and the Ethernet that we are simulated is probably this part, the determinism. So with this limit, it's possible to check if the scheduling is done right. In next figure, we can see the difference of a traffic simulation with and without jitter. So for example, in the figure above, we can see the traffic when jitter is half of the back, and in the figure below when the traffic is without jitter. So we can see the difference between them. Another part is the AFDX frame. In this part, we need to know that a data flow is uniquely identified within AFDX network by the set of UDP TCP destination port, IP destination address, MAC destination address, and the physical Ethernet connection of the receiving end system. In order to use the standard Ethernet frame for AFDX 2 bits, bit 40 and bit 41 of the 48-bit long MAC destination address have to be set to 1, always. For routing, all these addresses include a virtual link identifier with a size of 16 bits. So the MAC address must be a unique identifier. Also, it includes the information of which interface the package was sent from. Every frame has at the end of the payload a sequence number, just in front of the MAC CRC field. This number is bound to a VL and incremented with its transmitted frame on the AFDX network. Well, and about the work environment, we are going to describe the main hardware using the topology for the AFDX test. So we are using the Sync 7000 family. It's a family of system on chip, COC devices, developed by Schillings that combine programmable logic and with a hard code processing system. And the other part that we develop in this work is the Phoenicia board that was developed by Creative Electronic System. In our case, it's only in order to observe the reception frame circulation on the AFDX network. It could also be configured in transmission, but it would need to implement manually. So we can change some parameters. For example, definition bit by bit addresses, the checksum, something like that. In this figure, we can see two different developing boards. On the right, we can see the end system 2, Sync 7002. On the left, end system 1, the Sync 7045. And in the middle, the end system Phoenicia, that was developed by SIS. Yeah? To control our network, we use TT Ethernet. That is a fault-tolerant, security-critical, real-time communication protocol that integrates time-activated, speed-constrained standard Ethernet data streams into a physical infrastructure. So, in using this system, we can compare the real Ethernet with our simulated Ethernet that we are using in the AFDX network. And this is the part of the test result obtained. So the testing of our design was done first by test benches for each developed core. Then, to validate the whole system, tests have been created in software. There have been multiple tests for checking distinct parts, as we can see in the next table. They can be separately enabled in the main user task. All the hardware tests do not depend on the XML file and load specific data into the hardware. The other tests use the XML configuration for testing. For example, in the table you can see in the first row, a hardware test queuing with the function of test the transmission of queuing frames. So the demonstrator is based on AFDX message exchange between simulated end systems. In our case, the development of the FPGA system in the Sync board. The first step of validation is to check that the frames sent by the transmission part of the end system are compliant with the required AFDX standard. The main format can be analyzed on a PC connected to the AFDX network through its Ethernet interface. The Wireshark tool is used to expand the frame content and analyze in detail the conformance to IP standard protocol. Unless CATX can display the frame contents and show the part of protocols that stay common between Ethernet and AFDX. So this tool is not performing enough to catch all frames. Its time resolution is not precise enough to control the respect of back policy. So in this figure, you can see on the left an example of Wireshark tool display for a queuing frames for each end system of a SYNC 7045 frame associated to queuing port. And on the right, you can see an example of CATX display of capture frames of network B for end system SYNC 7020 for queuing port. On the left, in this slide, you can see another figure. This figure shows a console terminal for two development boards during normal execution. It can be noticed that printout does not discriminate the sample received frames from queuing ones. This should be part of our further enhancement. So this is only a basic system. Yeah. It's a simple implementation. Yeah. You can see that no erroneous frame is detected by the receiver, except, so you can see in the figure, that the first one received by the SYNC 7020 has an error. But this is due to the asynchronous application starting at both end systems. So when it's asynchronous, the first is erroneous. Yeah. And about latency, the latency measurement was made through the CATX tool by sending multiple frames in one window time frame, and then check how long it takes for the hardware to send a frame. The CATX displays the time between the reception of two following frames, also testing different lengths of frames. The proof values never exceed 20 microseconds for a maximal allow latency of 150 microseconds. So in the theory, we are speaking that we can see until 500 microseconds, but really in our system, we reduce the maximal allow latency at 150 microseconds. So in this figure, we can see that the transmission mechanism implemented with the hardware does not change fundamentally the footprint. So it's important to know that in these results, the implementation uses a COTS module for MAC layer. Its use is not optimized and covers wider user domains as the one really needed for AFDX for space. This figure shows the impact of the number of DL on the footprint. Note that the two curves on the left side, the light blue and the orange, show the fast increasing of the footprint with the amount of the queuing VL, since each VL needs a FIFO. So as a conclusion, after all the work, we can arrive to the conclusion that the demonstrator of the AFDX end system implementation over FPGA is possible. On the one hand, the design of the system gives a dynamic possibility, depending on the deterministic network result. So we emphasize this part. Deterministic is the most important part of this work. We can prove that it's possible. On the other hand, respect to the footprint measurements, the rise depends on sampling and queuing VL increasing number, being sample method the most efficient in FPGA due to the shorter FIFOs needed. The benefit of FPGA as communication based in satellite brings us a step further to the satellite technologies. the maintenance and or upgrades at distance, an option that can reduce increasing the obsolete number of satellites in this space. Moreover, a simple solution to add robustness against SEU, implementing directly in hardware a typical communication layer integrated mostly in software. Both benefits together allow the option to add higher number of redundant channels after the device is already on the space and allows the option to be adapted to the environmental exposition, reducing the risk of satellite designs. And that's all.
So, Pablo, thank you for your presentation, and I can open discussion. If someone has some question, you can ask. If not, I have some very fast question. You are designing your system for satellite onboard systems. So are there some requirements, for example, for temperature dissipation and so on?
Well, really, this system was developed only for airplanes because was a project approved for Airbus. But when we started with the first result, we realized that it was possible to adapt to another system like satellites. So maybe we need to investigate, to research more about the latency, for example, because this point is very important in satellite communication, and in airplanes is not so important. But in the rest of the system, the network, the elimination of the ACQ signal, for example, that is typical in Ethernet, and in AVDX is not necessary, permits to imagine that it's possible to use in satellite also.
Okay, thank you for answer. And if there are not any other questions, we can move to the next presenter, which is Ken from the Turkey, and his contribution, a fraction order sliding mode controller design for trajectory tracking control of an unmanned aerial vehicle will be very interesting. So, work is yours.
Thank you, Mr. Chairman. And can you hear me?
Yeah.
Good afternoon, everyone. My name is Can. I'm from Turkey. I am a PhD student at Atatürk University at Department of Electrical and Electronics Engineering. Today, I am going to present our study, which is titled as a fractional order sliding mount controller design for trajectory tracking control of an unmanned aerial vehicle. And here is the outline of my presentation. First of all, I will mention about our system. Then I will give and present the structure of our unmanned aerial vehicle. Then I will present the nonlinear equation of the motion of our system. Then I will explain our proposed controller method. Then I will present the experimental results, and I will complete my presentation. And first of all, in this study, we have proposed a fractional order sliding mount controller and to apply a four-rotor unmanned aerial vehicle, which is known as quadrotor, to perform trajectory tracking for different time-varying references. Because this type of systems have nonlinear systems dynamics, which are affected by external disturbances and parameter variations easily, we have proposed fractional order sliding mount controller instead of its integer order 1. We use this fractional order controller due to its providing more flexible control to our system when we compare its integer order one, and we hope that we utilize its disturbance rejection characteristics to keep our system on desired trajectory, as well as to overcome parameter variations. The dynamic model of our system, the quadrator's dynamics is similar to the motion of an object which has 6 degrees of freedom in space. First of all, we have to mention about the body axis and inertia axis relationship. So we have the inertia axis, which represents in our study I matrix, represents the inertia axis, and B represents the body axis. In addition, both described axis and experimental setup used in our study given in figure 1. And the position of our quadrator is presented by Kıssi matrix and linear velocity by Y matrix and Euler Angel matrix by eta matrix. The relationship between the body axis and Earth Earth axis is connected by a rotation matrix, which described as R in our study, and the angular velocity represented by omega matrix. Thus, the quadrature dynamic equations and the whole dynamic equations can be described in equation 1, which is given in our study like this. In these equations, the T represents the total thrust force generated by each rotor. F represents the lift force generated by each rotor as well. G represents the gyroscopic torque, and tau matrix represents the total torques of our system. The reference position and reference angles also defined in equation 2 as given here. These are reference position, which means through the X, Y, and Z axis, and eta matrix represents the Euler angles, which is known as petrol and yellow angles. And then the error signals which occur while trajectory tracking can be defined in equation 3, which is the position error, linear position error, and linear velocity error. And this error represents the Euler angels error, which means the Euler positions and angular positions and angular velocity errors. And taking time derivative of the both controller error signals, the following equation can be obtained. And using these equations, we can define our system mathematically and control our system easily. From equation 1, the dynamic equations depending on the Kıssi and eta, which means the position, the second derivative of the position and second derivative of the angular Euler angels. We have divided our system inner loop, outer loop, cascade structure. Therefore, we have two different systems, and doing this, we can easily control our systems better. To connect our two different subsystems, which is known outer loop and inner loop, we have to define a connection term, which is used in our study, a virtual control vector, to join the system in the cascade structure. After this definition, the open loop system can be obtained as in equation 5 easily in terms of position vector and angular velocity vector instead of the whole equations which is given in equation 1. Here, this term which B1 times T over M R AZ minus G AZ minus gamma equals to F delta term, which is unifying term, express the connection between the inner loop and outer loop subsystems. And we analyzed the study for the virtual control signal can be written as in equation 6. These equations give us the reference Euler angles for our inner loop. The controller design. First of all, we introduced the fractional calculation, which is very attractive method to obtain more sensitive control achievement. The fractional order control provides us more flexible and define our system very well instead of its integer order. And so we, first of all, we define a differential operator for a general fundamental operator. Here, the limits of the calculation are denoted by A and T respectively. Also, P represents the fractional order. To obtain the fractional order sliding mode control, a second order system is defined in equation 6 to obtain control algorithm, and its parameter error can be expressed as in equation 9. The errors of the system along the x, y, and h axis can be written as given below. Here we define the all three errors because we control our system's position and we have to define the errors of our system. And then using x dot equals to y transformation, the system can be rewritten as a first order system instead of the second order system, which is given in equation 11. And then we can represent the whole equation as a state space model. And it's a simple structure which is given in equation 13. And to obtain our control method, the sliding surface must be denoted and defined as in equation 14. After defining the sliding surface, the sliding function must be expressed as given in equation 15, which represents by sigma. Here, our sliding function, depending on the time and the states of our system, and also we can take in time derivative of our sliding surface, we can obtain the fractional order sliding surface, which is given in 16. To obtain the sliding mode control signal, we have two different phases, which are called the reaching phase and switching phase. To obtain the reaching phase, before we have defined the reaching law to reach the sliding manifold and to keep the system on the sliding manifold. And doing this, we have to define our equivalent control, which is given in equation 17. And we can use the previous equations into the 17. We can obtain the equation 18. The control signal, named as reaching signal, can be derived by means of a positive definite Lyapunov function, which can be selected as in equation 19. And taking time derivative of the 19, the equation 20 can be obtained. To solve this equation and obtain a control law, we also take in consideration of a solution which is given sigma x equals to 0. The equation 21 can be obtained, and we equal to each other this the equation given in 20 and given in 21. The equation 22 can be expressed. Here, D represents the fractional order operator, and Q is represents a positive definite matrix.
Sorry, try to be a little bit faster.
Okay, so for this equation, from this equation, and we can achieve the 23 equation, and using the previous equations and replacing into the equation 23, we can obtain the control signal, which is given in 26, U equals to equivalent plus K sigma. Here, K represents the constant. We can select this constant very well to obtain more suitable control signal. In our system, the sliding mode controller has this effect, which is called chattering. Therefore, we prefer to design 28 with a low-pass filter, which is the average of the sum of all equivalent control signals in the system to overcome these unwanted effects. And to obtain a low-pass filtered control signal, we define and we select U equivalent plus delta U as equals to 1/1 plus tau s U, and then we write these equations into control signals. We achieve the control signals as given in 28. And from using this whole short algebra, we obtained all control signal as given in 31, 32, and 33, which is called the virtual control signals defined before. Here, the control block diagram of the system is given. As seen from this control block diagram of the system, here we controlling the position of our system and generating the virtual control signals to send the inner loop of our system. Here are experimental results. We given our system two different references. First of all, the inclined circuit rota. The left one, which is given in figure 3, the result of fractional order sliding mode controller. The fourth one is the integer order sliding mode controller. To see clearly, we can check its direction performance x through the x, y, and h axis. As seen from the figures, the fractional order sliding mode controller has better results while tracking the trajectories. When it compared with the integer order one, we can see some deviations clearly from the results of the integer order sliding mode controller. Also, the generated control signals checked, the fractional order controller has produced low magnitude control signals, which is suitable for our system when it compared the integer order control signal. And also it produce more suitable corner signal forms as seen from the gamma 2. Also, we have applied the zigzag rotor reference, which is given in experimental results part, and to control x and y axis performances our control systems. As seen again, x, y, and h axis performances, the proposed control method has better results in terms of tracking the references with less deviations, as seen from the figures as well. And also the proposed control method also produced the control signals to overcome the parameter variations and to keep our system on desired way very well when it compared the integer order sliding mode controller. To complete my presentation, we have proposed the fractional order sliding mode controller and applied to quadrature to indicate its fractional behavior against disturbances such as sensor noises, contrary wind effect, as well as the robustness to parameter variations and trajectory tracking performance. And also to compare the proposed controller, the integer order sliding mode controller has been implemented on the quadrature for the same rotors to control of this unstable system. The experimental results show that the proposed controller has less trajectory tracking error with small deviations while tracking the inclined circle and zigzag rotors, whereas the integer order has more tracking errors as well as having more overshoot and undershoot. Also, the fractional order sliding mode controller has less time delay and produces lower amplitude control signals, which is very suitable for our inner loop to produce needed error angles for the system. Moreover, the control signals produced by the both controllers have nearly the same chattering level when compared their trajectory tracking performance. Here are my references, and thank you for your attention.
Thank you for presentation, and we have delayed, so very short question if there are some. So there are not questions. I think if someone has question, you can write directly to colleague and they will respond on them. So thank you again for your presentation, and we have to move to the presentation from Dmitry Chulkov from Latvia, which has an title Comparative of MEMS and fog gyroscope for daily use in the camera stabilizing systems. So, word is yours.
Yeah. Hello, everyone.
Thank you.
My name is Dmitry, and I will replace Mr. Alan today. And I will start with a short introduction. Our research reviews fiber optical gyroscope implementation for camera stabilization systems. The main point of the research was to determine whether the implementation on Fox sensor will increase performance of the entire system compared to a cheaper MEMS sensor. We performed several tests during this research, and all tests were aimed to be as realistic as possible in order to evaluate sensor behavior in situations that are close to real life. And as I said, the introduction of the need of this research is that the need of camera stabilization appeared together with the first camera itself, and it started with a similar tripod device, and it was almost impossible to take a picture without this stabilization. The modern stabilization systems are far more advanced and complex, and is used mostly to improve the quality of photo and video material. The as fiber optic gyroscope has an extremely precise rotation rate, high performance, and long lifetime, we decided to compare it with MEMS sensor to evaluate if it's worth to implement in camera stabilization system. The research was performed by two different types of inertial measurement unit sensors coupled with stabilization controller. Now, maybe you can see the stabilization controller itself and the original MEMS sensor. Okay. In the beginning, we used fog and IMU separately to evaluate the quality of stabilization just visually by filming different objects in laboratory environment in the repeatable manner. The results was almost the same. However, this test had a lot of variables, as you understand, like the gimbal hardware itself, because the smoothness of stabilization also depends on the stabilization controller, on the motors, and a lot of factors. So we decided to compare only the received data from both of these devices. And one of the interest points of our research was to compare devices' immunity to vibrations. So each of devices was sequentially connected to the controller, and the graphical user interface was used to compare data from fog and MEMS EMU. Both devices were placed on the same surface with small intensity tapping applied to produce vibrations along the surface. And then here you can see the chart of the received data. The result certifies that because of no mechanical moving parts are used for fog sensor, it lacks of cross-axis sensitivity, acceleration and shock. However, despite the fact that received data from fog and MEMS IMU has such difference, the visual evaluation of the picture had not such a difference. It could be also explained by the stabilization controller that just ignores some minor vibration data from IMU or with the camera stabilization mechanism itself. The next step for us was to compare the difference of the received data from fog and MEMS IMU. In order to perform such test, we have connected both devices to controller at the same time. So if this chart was sequentially connected, so we received from one device and then from other, in following tests, we will combine all the data from both devices. And as you can see, here is also the comparison of the size. The big one is the optical gyroscope, and this is the MEMS gyroscope. And one of the biggest problems during this test was related to the alignment of devices, because the resulting output data can be dramatically influenced even by a slight difference of the axis position. So we needed to do a proper alignment and firmly fix the both devices. Also, after several tests were performed to make sure that acceptable alignment has been achieved, and the difference in the readings does not exceed it of 1% to proceed with the final comparison test. And here we can see the part of the final chart with here the aligned construction was rotated multiple times in the opposite directions, to imitate the sudden direction change. For example, when you are filming from the speedboat or some very fast moving object with sudden direction changes. And in that case, the stabilization system should help the operator to preserve the smoothness of the video. In order to make test results more realistic, the rotation was performed manually without any rotational devices or motors. So what we can see is very unpredictable and randomly applied forces. And here you can see, I will zoom it for better. Sorry. Yeah. You can see the partial plots of measurement results where gyro readings refer to the fog IMU, and the accelerometer lines represent the difference between readings of fog and MEMS IMU. The difference in the received data can sometimes can be very insignificant, as we can see the example of the readings of z-axis, and here it is almost identical. But sometimes the error appeared quite a lot, and but in average, the difference in reading between fog and MEMS-based IMU was roughly about 20%. Such difference in readings was mostly caused by rotation of device in opposite directions. So when you change the angle of rotation, the MEMS IMU continues to has inertia, and this causes the error in the readings. But the fog sensor has not has inertial resistance to the movement, so it can read the data more precisely and faster than MEMS IMU. But as I have said, the difference in readings was only about 20%, and as far as you know, the most operators do not suddenly run in opposite directions when they're filming. So the point of using of fog IMU is only recommended for specialized equipment where precision and reliability is a must-have factor, and it is used in extremal environment. And for example, the military-grade equipment or so on. And also the fog IMU adds to the system overall weight, since MEMS-based IMU solutions are more compact and lightweight. So it is open question of what parameter is more valuable to end user, and the other important aspect is the price, since MEMS sensors are approximately 10 times cheaper to produce and purchase, which makes them perfect candidate to be used as electronic components for mass production devices. In fact, the price of MEMS IMU allows you to add even extra components such as magnetometer, barometer, and accelerometer that will give auxiliary data for stabilization controller. And it can be used to improve the whole system quality. So our conclusion is that the folk IMU is good, but it is not worth to implement to the mass produced gimbals. Thank you.
Thank you for your contribution, and I open discussion. If there are some questions from colleagues, please ask. And more during that, I have some small question for you. Are there any significant differences between expenses of standard MEMS-based and also fiber optic-based approach?
Do you mean time expenses? Price?
Mm-hmm.
Price, it is very significant. For example, this fog sensor we were provided was about 600 USD. The MEMS sensor we used originally from this stabilization controller is about 40 USD if purchased separately from controller. But it is also provided into kit. In fact, the whole stabilization controller was much cheaper than this fog IMU.
So, okay, thank you. If there are not any further questions from the audience, we can move to the next presentation, the last presentation, which is given by Jehan Akbar from Pakistan, and the title of the presentation is Aluminium, Gallium, Indium Arsenic, Indium Phosphor Base 5 and 3 Quantum Wells Mode-Locked Laser Diodes. It is comparative study. So the word is yours. You can introduce your work and show us the results. So please use the full screen view. Thank you. You have to switch on your microphone.
Okay.
Yeah, now it is working.
Okay, perfect. Thank you very much. Thanks for giving me a chance to present my work here in this international conference. I'm very thankful to organizers to organize such a great conference in these hard times. Today I'll be talking about comparative study of 5 quantum wells and 3 quantum wells mode-locked lasers. So this work is basically based on 2 different types of lasers. One laser is based on 5 quantum well material. The other lasers are based on 3 quantum well materials. And here we compare the performance of both types of lasers. Okay. Motivation of this work comes from the application of high power lasers. High power mode-locked lasers, the lasers which emit short optical pulses, they are used for terahertz radiation generation. They are also used for OCDMA in optical communication systems. They are also used to exploit nonlinear media and also for pumping of different types of other lasers. So if you start counting the application of high power lasers, I think there are numerous applications of high power. I'll not go into details. But what happens is if you have a semiconductor mode-locked laser, you want a high power operation of the semiconductor laser, you have to inject more current. Problem is when you put more current inside the laser, the pulses become broader and broader, and at a stage come when the laser is not mode-locked. So you have to trade off between the power of the laser and the performance as a mode-locked laser. So you cannot increase the current after a certain point. And also in my lasers, I have made efforts to increase the output power of lasers and also improve the coupling efficiency of the lasers and also increase the mode symmetry, which is required for coupling of lasers with optical fibers. The basic idea of my devices come from the wafer structure, which I have used for fabrication of devices. The wafer structure available in the market is the IQV standard material, which the structure is shown here. The structure is basically the conduction band diagram here, which I have presented. So if you look here carefully, you will see the number of quantum wells are 5, which are aluminum, gallium, indium arsenide, the 6 nanometer thick quantum wells, and also have quantum barriers. I have made a very little modification to this wafer structure. I have decreased the number of quantum wells from 5 to 3 in order to increase the differential gain of the material. And also in the inside substrate, I have included a far field reduction layer. The far field reduction layer increases the spot size of the laser, which increases the coupling efficiency of lasers with optical fiber. So this is the improved wafer structure. The number of quantum wells are decreased. The far field reduction layer is inserted, which is 160 nanometer that is inserted in the enclosing region. So two modifications, the basic modification are only two. For the far field reduction layer. See how before I present the result of my device, first let me briefly introduce mood locking. Mood locking is a technique which is used to generate short optical pulses from lasers. So it is based on locking the phases of different modes, and you get short optical pulses. By short optical pulse, I mean picosecond or femtosecond optical pulses. This is the schematic of the mood lock laser. You can see here the length of the device is a few centimeters. I have two sections of a simple mood lock laser. One is gain section and the other is switchable absorber section. Pulses, optical pulses are generated in the gain section, while the switchable absorber section is used to reduce the width of the pulses and also to give shape to the pulses. If you look at the cross-sectional view here, this is the cross-sectional view. I have a ridge waveguide. This ridge waveguide is fabricated using lithography technique, electron beam lithography. And this ridge waveguide is used to find the optical modes here. You can see by red color, I have shown a here. So this is basically introduced a step of refractive index. And because of this refractive index step, the optical mode is confined under this ridge waveguide. And the frequency of the laser is also a very important factor. In case of, in the course of this work, I have fabricated 40 gigahertz lasers, but you can change the frequency of the laser just by changing the length. If you look at this formula, you have the frequency is dependent on the length of the laser inversely. So you reduce the length of the laser and you increase the mode locking frequency. But there is an upper limit on this. You cannot increase the frequency above a certain point, and the upper limit is because of nonlinear effect. So if you want to have a very high repetition frequency, you need to use harmonic mode locking. Okay. Before we build the device, we do the simulations, and for the simulation, we use commercially available software, which is beam propagation simulations. And on the left side, I have shown the simulation result. So my simulation results are telling me that if I have a ridge waveguide, which is around 2.5 micrometer wide, and which is 1.92 micrometer deep, then I will have a very stable single output laser. And you can see the laser output is very stable and it is confined under the ridge waveguide. And also I have shown this scanning electron microscope picture of the ridge waveguide. So I have a ridge waveguide which is around 2.5 micrometer, and I have used the silicon dioxide as insulating material, and I have used HSQ. And also you can see the active region in the far field reduction layer. So light is generated and it is confined inside the active region. Okay, now as I told you, I have fabricated first I did some modification in the wafer structure which is available in the market, and then I fabricated lasers from the wafer structure which I have modified and from the wafer structure which is already available in the market. So the one available in the market is shown with the red color, and the structure I have developed is shown with the black color. And you can see from the 5 quantum bill which is shown by the red color, I can get a maximum output power of around 30 milliwatt. But from the wafer structure, from the device which are based on the wafer structure, we have modified, and that is only 3 quantum wells. You can see the output power is around 68 milliwatt. So you can see around 2-fold increase in the output power of the laser. So by decreasing the number of quantum wells, we have increased the gain of the material, and the gain of the material has increased the output power of the material. So this is only the output power measurement, and this is the basic goal that I wanted to have a more powerful laser. But I have to check that, okay, I have got increase in the output power, but what is the effect on optical pulses? Do I still get short optical pulses? Is the device mode locking or not? So in the next couple of slides, I'll be showing those results. This is the experimental setup I have used for mood locking characterization. I have my device. The device is supplied with the current, the gain current and stable absorber voltage in reverse bias, and the light from the device is coupled in the optical fiber, which is shown in the picture. And also in the picture, underneath, I have shown that the device is emitting light. The light from the device is collected through isolator, and then the light from the device is coupled into the optical fiber and then use a 50-50 splitter. So 50% of the light is going to the optical spectrum analyzer, and the rest of the 50% is going into intensity autocorrelator and auto spectrum analyzer. So using this experimental technique, I can simultaneously measure the optical spectrum. I can also measure the autocorrelation trace and the RF spectrum. And these three are required in order to properly characterize the mood locking performance of the device. These are the results. So the mood locking results on the left side, I have the results from the 3 quantum well material. On the right side, I am showing you the results from the 5 quantum well material. And this is the single pulse emitted from the device. So you can see that the device based on 3 quantum well, I'm getting 900 femtosecond, 0.9 picosecond wide optical pulses. While from the device fabricated using 5 quantum well, I'm getting 1.3 picosecond pulses. So this clearly shows that the 5 quantum well material lasers are emitting very broad optical pulses as compared to the 3 quantum well lasers. Now let's compare the optical spectrum. Optical spectrum is really important. And you can see, the wide optical spectrum, the better, because, wide optical spectrum and shorter optical pulses basically are required in order to have transform limited pulses. So you can see on the right side, I'm showing the optical spectrum from the 5 quantum well. On the left side, I'm showing the optical spectrum from the 3 quantum well. You can see from the 3 quantum well, I'm getting wider optical spectrum, which is giving me a 3 dB bandwidth of 9.2 nanometers. While from the 5 quantum well, I'm getting 5.5 nanometers. So this is almost double. And, I'm getting transform limited pulses. Now let's compare the RF frequency bandwidth. The radio frequency bandwidth emitted from the 3 quantum well lasers is 130 kilohertz, while from the 5 quantum well lasers, that is 900 kilohertz. So the quantum well devices are giving very good optimal performance, increase optical spectrum, decrease RF bandwidth, and decrease optical pulses. Now let's compare the mood locking performance. That, because it is very important that the device should emit short optical pulses over the wide range of bias conditions. So here I have shown the performance of the lasers for different bias conditions. I'm changing the gain current, and I'm also changing the switchable absorber reverse voltage. And you can see the 3 quantum well lasers is mood locking. It is giving me short optical pulses over a wide range of bias conditions. But if you compare with the 5 quantum well lasers, the bias conditions are very low, and it is very, very, very narrow region where the device is showing me the optical mood lock. Okay. If you call part of the presentation, I have 2 modifications to the reference structure. The first modification is I have decreased the number of quantum wells, and you have seen decreasing the number of quantum wells in the form of improvement in the mood locking performance. And I have also made another modification, which is insertion of far field reduction layer. I have reduced the far reduction layer, which increases the near size and which reduces the far field. So in order to find the far field, this is the experimental I have used of my device. I am trying 3 quantum wells. the far 3 quantum mill. On the right side, this is the far field of the 5 quantum mill. On the upper side, you can see the 2D and 3D view of the light emitted from the 3 quantum mill material. You can see the mode is very symmetric. It's nearly symmetric. It's very stable, and also it's more circular. So more circular is required for improvement in coupling efficiency with optical fibers. And also, if you measure the divergence angles, that is 23 degrees into 26 degrees, while that from the 5 quantum mill is 34 degrees into 35 degrees. So by insertion of far field reduction layer inside the 3 quantum mill laser, I have significantly improved the far field, which have improved coupling efficiency with optical fiber with 53%. So with the 5 quantum mill laser, the coupling efficiency with the optical fiber is only 37%, while with the 3 quantum mill, the coupling efficiency is increased to 53%. Okay, with this, I will conclude my talk. I have designed a novel epitaxial structure with 3 quantum mill inside the far field reduction layer. The device fabricated with this novel material provides me higher output power. It also increase a larger bandwidth of short optical pulses and narrow alignment. It also gave me a wider range of mood locking, as you could see from the mood locking maps. It also decreased the far field pattern and increases the coupling efficiency with optical fibers. And also the mood locking is more on a wider range. And thank you very much for your patience in listening to my presentation. Thank you.
Thank you for your presentation. And if there are some questions from the audience, please ask. If not, I have very short question. Is there some possibility how to make a dimension and the height of the device a little bit smaller? Yeah, we saw some photos where just the device was designed and measured, but it seems to be a little bit bulky. Is there some possibility how to decrease the dimensions of such device with which cost?
Okay, thank you for your question. Actually, your question is, can we decrease the dimensions of the device and still get the same performance? Well, the dimensions, you know, here we have to be very careful about the dimensions of the device, because if we increase or decrease the length of the device, it's going to change the frequency, the repetition frequency. And the target of this work is to have a high frequency laser, which is 40 gigahertz. And this laser is meant for optical fiber communication systems. So 40 gigahertz is used, it will be used for the future telecommunication system. And if I decrease or increase the length of the device, the repetition frequency is going to change. So this depends on my requirement of the repetition frequency. Okay, if you ask about the dimensions of the ridge waveguide, if I change the dimension of the ridge waveguide, it is going to change the performance of the device in terms of number of modes, because it is optimized wafer structure, it is optimized ridge waveguide. So if I reduce the height of the ridge waveguide, it will support more modes, and that is not ideal for coupling with optical fibers.
Thank you very much for your answer. If there are not any further questions from the audience, thank you for your presentation again. It was very interesting, and my pleasure is to conclude this session because the time is up. So thank you again to all of us, to all of you for the attendance and your interesting contribution at this section. So goodbye, and we will see on the next conference.
Thank you, Mr. Chairman, for sharing participants. And after half of hour, we will back to closing session. So you can stay connected and just turn off video for a short, because we will make a global image of all participants. So I would be glad that you will take part in this closing session. Okay, so thank you again.
Thank you.